Everyone, welcome to this episode. In this episode, we're going to talk about spatial smooth constraint. So let's recap the last episode. In the last episode we talked about matching cost function and the way how it works, the procedure how we do this matching. So I will show you this system block diagram. This is system block diagram for the whole FPGA code. So we have already talked about census transform, and the output dimension memory layout looks like this. It's the image, and each one is 63 bits, and the original image, left and right image, is 8 bits for each grayscale image. After input to this matching color cost block, the output is the depth is 64 times 6, because 2 to the 6 power, 2 to the power of 6 is 64. So let's recall that this is the corresponding position of this from the left image and the right image, right? And we're looking to the left, and the Dmax is 64. It's not bit. Sorry, I made a mistake. So you have 64 corresponding searching positions to the left. So that's the disparity, the maximum disparity. Okay. And now today we're going to add spatial constraint term, because we've already talked about that it's not reliable, it's not enough. Okay, sorry, my poor English. So color feature alone is not enough. We need more constraint. So now we're adding the spatial constraint term here. We were going to explain this in detail, okay, in this episode. And this is system diagram. Today we are going to prepare for this module. We're not going to talk about this module. We're preparing to something, adding a spatial constraint in terms of penalties. We're going to prepare for this one in this episode. So adding depth smooth constraint, the this term is a color constraint, and this term is a spatial smooth constraint. We assume that in a space for every surface, most of them are continuous. So we can add such a constraint. This constraint is we can select a small area around this pixel. For each pixel in the image, we can select a small area like this one. It's 3 times 3. Okay, so you have the 8 neighboring pixel Q. Okay, Q, and because it's for most of the surface is continuous, so their distance should be small. If the distance is large, it will give the penalty. It means that when we're looking for the minimum, global minimum, it will, because it's penalty term here, it will automatically shifting to the place that make this cost to the minimum, approximately minimum. Okay, so that is this is spatial smooth constraint. Since the z is a function of d, and d remember that d is disparity, and is inversely proportional to d, and each d it's quantized because D is pixel, right? Here we are talking about the not continuously. It's the pixel is quantized 1 bit, 2 bit, and okay, 1 pixel, 2 pixel. So since D is quantized, so and the ZP minus ZQ is also quantized. So the distance, the depth is also quantized. We have already talked about that in several episodes ago, that far away the quantization error is much bigger. Smaller, much more near the quantization error is smaller and smaller, and to be very precise, when it's in an optimal observation area. So for every stereo vision camera, they have the most further away distance and also the close distance. So it is an observation range and depth. Okay. Okay. Now let's okay. So now, if you do the little math here, you will have this conclusion that I'm not going to write this because you can. It's pretty simple to verify that in two cases. First case is this one, and second case is this one. Okay, if ZP is greater than ZQ, and ZP is less than ZQ, in both cases, you will have this conclusion that the delta disparity increase, then the distance, distance in two adjacent pixels is also increased. The discrepancy also increase. So we have this relationship between this D and Z. Okay, so then since it increases, and then it also increases. Okay. Now, since this is quantized, and also we don't want use Z here, we can substitute D here, disparity here, because disparity number is much easier because it's derived from the pixel, so you don't have to do much difficult math using. If you use Z, you have the much difficult math. Okay, but since you have this relationship here, so what we can use use dp to minus dq to substitute to this term and to become this. And also because it's quantized, then you have to, the difference is maybe it is one, it's 1, 2, 1, 2 or 3, and we only allowed it to be 1. Maximum difference should be 1. So we give it a little smaller penalty, P1. But if it's greater than 1, then I will give you a penalty P2, which is much bigger. Okay, so this continues from this original continuous term to become this quantized term. Okay, so I think it's quite straightforward to understand this spatial constraint, spatial smooth constraint, and because it's quantized, so we can write it in this quantized way, and first it's the disparity is 1, and we'll give it a smaller one, and greater than it P2. It's much bigger penalty. And how do we minimize the cost function? Of course, not doing things like this. It would be horrible. And we will talk about in the next episode that we're using dynamic programming, and this actually is a quite interesting optimal method. It's different from the first order gradient descent method that widely used in deep learning training stage. Also different from the second order Gaussian-Newton method and its variants that widely used in computer vision algorithms in order to find the optimal solution. Apart from the accelerating its own FPGA, we're going to accelerate this dynamic programming on FPGA, but also the dynamic programming method that we used here to find approximate optimal solution. It's quite interesting itself. We use a lot of assumptions. For instance, we decompose. We will talk about this in the next episode. We do this we make some assumptions that one tone can be decomposed into multiple tones, the summation of multiple tones, and in order to find the optimal solution to E, which seems like a chicken and egg unsolvable problems. So we will talk about these chicken egg unsolvable problems next episode. Okay, so that's it. That's the today's this episode about. Thanks for watching.